The last thing I'd like to talk to you about today is exponential growth and how we model that with a continuous model. What we've been using in just the two examples we've looked at is really a discrete model. We're taking snippets from what happens at the end of a cycle, a year cycle, a 2-year cycle, or something like that. We can use functions and then graphing calculators and things to draw the answer and realize that that's an approximation with what's going on. And then what I'd like to talk about with you, though, really is, okay, how do you do that? You know, if you've got some kind of population growth, how do you do that? Okay? So, and I want to talk about two situations, unrestricted and restricted models. Okay? What we just looked at, actually, with that Leslie matrix was an unrestricted growth model. And it was actually exponential growth because the rate of growth actually did depend upon how many cows or whatever it was I had. And that is what we call exponential growth. That's when the rate of growth is the rate of growth of an amount is proportional to how many you have. Now, that type of situation, and we've talked about this previously, can be modeled with an exponential function, e to the kt, where k is the rate of growth, and a sub 0 is the initial amount that you start with. In fact, on one of the previous episodes, we talked about how when your step gets smaller and smaller and smaller, you get this function e to the kt. So we have kind of talked about this in the past, but now the problem with this, and I discussed this in the last example, is, well, you're assuming here that they can grow without bound, that I have unlimited resource for sustaining growth. Now, I just want to take a second and prove to you, just show you that this model does what I'm saying it does. If I let the initial amount be 1 and I let the growth rate be 20% or 0.2, here is a graph of that curve. And you'll notice the initial amount is 1. And if I take little snippets, you know, if I take the rate of change can be construed, and we've talked about this previous, as the slope of a tangent line. So if I took the tangent line at this point, and I'm just approximating it really, and then I took the slope of this, okay, the slope is about, at that stage is about 0.2, okay, and you can get that by taking 2 points on the curve and calculating the slope. And then if I look at the function value right there, and I multiply by this rate of growth, this k, well, the function value right there is 1, so sure enough, these things are equal, and that's what I said they ought to be. If I take the tangent line a little bit higher up, say at when t is 6, okay, the slope of that line is almost 2/3, 0.664 or so. And if I look at the function values right there and say 0.2 times that function value, sure enough, I get 0.664. So they are matching up. That's what's supposed to happen, okay? Now, that's a good financial model. We've used this when talking about money. And boy, you like to think your money can grow without bounds. But it is a bad population model. As illustrated in the previous example, you can't just assume that things can just grow, especially living things, because they have to eat, they have to breathe, they have to drink, they have to have water, and they have to have medicine sometimes, things like this. So we need to look at a model where the resources are capped. You have some kind of capacity for things living in an environment. Okay? So that's the next example. That is restricted exponential growth. This is where the rate of growth of an amount is proportional to the product. You take them and multiply. It's proportional to the product of the amount and the amount less than the carrying capacity, which I'll use a capital K for that because I didn't want to use C, I guess. But there's some high number that I'll say that's the most you can have. That's it. And after that, things start to starve to death in business like that, or die off in some way, die of disease or whatever it is. Now, the model for doing this is messy, but and actually deriving that requires some calculus, so I'm not going to get into the derivation of it. But it's this kind of, there is a pattern to what's going on here. This is called the logistic equation, and this is something that you'd be given to use as a model in some type of situation. We just have to fill in the blanks. A sub 0 is our initial population, K is the carrying capacity, and this K It's not the growth rate anymore, but it is some kind of constant that we would need to solve for. Okay? So let me just kind of convince you quickly that it does what I'm saying it does. I'll let the initial growth, the initial amount be 1, k be 0.5, and the highest amount be 10. If you graph this, you'll notice that here's 10, and you'll notice that as it gets closer to this 10, it's leveling off. Okay, I've kind of filled in the blanks here. And sure enough, that curve is doing what I said it would do. In fact, if I check the tangent lines, the slope here is about 0.45. This is when time is 0. And if I take the amounts, here's the amount, and here's 10 minus the amount, that would be 1 times 9. Solve for n, it's about 0.05. Well, if I check in a different location, this is when time is equal to 6. The slope of this line is a little bit over 1. If I say 0.05 times the amount of that curve, the y value of that curve, and 10 minus the y value of that curve when time is equal to 6, sure enough, I get the same amount. So it's doing what I said it would do, but what I'd really like to do is show you how that can then give you a realistic model of populations. So let me give you an example. Let's say you have 40 cows like the previous example we talked about. I'm not going to worry about tracking them by age group anymore. I'm simply going to say, all right, I've got 40 cows here. I have the capacity to feed and sustain 100. Okay, that's all the pasture I've got. That's all the feed I've got. And then I'd like to know, okay, I do want it to grow. I do want my numbers to grow. So if I have, say, at the end of the year, I have 44 cows. Okay, that's going to give me an indication of my growth rate. When can I expect that herd to grow to 80 in number? Okay, so we're going to use this logistic equation to model the situation, and what I'm going to do is I'm going to plug in the values. My initial population is 40, so 40 would go there, 40 would go there, and 40 would go there. My carrying capacity K is 100, so I'll put 100 there and 100 there. And that I don't know K yet, so this actually kind of works out to this. I've simplified it a little bit. What you have to do is use that bit of information, okay, I have 44 at the end of the year, to solve for K. And this is quickly just some solving exponential equations. We do this in college algebra. Kind of clean things up. You can actually kind of switch those things out, clean that up and subtract the 2 from both sides. Go through then and divide by the 3. And then to solve for K, you take the natural log of both sides. So you get a negative K equals this, and K then would be a negative this thing, or it just turns it upside down. That's about 1.6303. And then you use that in your model and set your model equal to 80. So, and I know I'm doing this very quickly, but you've seen this before. It's the same steps. You just take things, swap them out, subtract 2 from both sides. You get this down to an exponential thing, take the log of both sides, and you get K to be about this kind of messy thing, but it's about 10.9 years, and I'm relying on my calculator to get that. And very quickly, I'll just show you the graph of things to convince you that that is the correct answer. Here's the curve that I graphed. Here's 80, and it does hit about 10.9 right there. Okay, a good example of how we can get a realistic model using exponential functions. We've got a couple summary pages, and we'll come back and wrap things up.